Let's get rid of that. All righty. Oh, my notepad should be getting pulled up here. Awesome. Okay, cool. Everybody can see that, right? I can see it, so I assume everybody else can. So we'll go from there. All righty. So block 3, magnetics. Obviously, this is a massive block, right? Lots of stuff to worry about in this chapter, right? But we've broken out into each of the topic sections, right? So A through F, I believe, is what we have. So that covers everything from the Biot-Savart law to Faraday's law, things like that. So the way these notes are structured, there's a great conceptual overview, but also some examples that are trickled in here. There's just so much material to go over. We can't go over every single example as we're going through it. So I'm going to skip some of them for now, and then we'll go back later and do some examples based on the vote that you guys cast, right? So don't worry about that. And they're also there for your reference. They're very well worked out, thanks to Nick. So they shouldn't require too much help to get through. But other than that, this is kind of how we're going to go through things. So without further ado, let's get into it. All right. So the first topic in block 3, sorry, this is kind of laggy, is with the Biot-Savart law, right? So just in general, right, dB equals mu naught I times dl cross r over 4 pi r cubed. So this formula is used whenever we have obviously a differential magnetic field, right? So examples include, remember from that studio, right? If you had kind of a graph that looked like this, the function like that, and you wanted to find the B field here, for example, right? I believe that example was used quite a few times, both in the greater group activity, things like that. These are situations where we would use the Biot-Savart law, right? Where it gave us maybe some current function, or so on and so forth. This should look hopefully kind of familiar back from Unit 1. It's supposed to be the magnetics equivalent of Coulomb's law, or at least close to it. Major differences include this cross product here, obviously. But other than that, the problem solving process is very, very similar to that, what we'd see in Coulomb's law. I usually like to go through these just kind of step by step. So I'd look, and at first I would probably find DL or R, right? And then take a cross product based on that, and then plug in all of those other variables and integrate to find B field. So very, very similar problem solving process to Coulomb's law. Like I said, they're very well translatable over and over again. Other than that, I would say if this problem ends up being the free response question, I have to be honest with you, I'm not entirely sure if there will be a free response question or not. I'm not up to date on that. Nick, maybe you can answer that better than I can. But if there's a free response question, it very well could be the Biot-Savart law, right? So just make sure, again, to show all your steps, all that good stuff. And see what I was going to say. Yeah, I think that's it. Yeah. So again, I apologize. I'm not 100% sure about the status of the free response question. It should be there because we're still able to grade those, but not positive. So don't take my word for it. But yeah, other than that, I will move on a little bit from the Biot-Savart law. Right. This is one of those examples I was talking about. Should look familiar because we did it in studio, but it's very, very nicely worked out here according to what the solution should be. So I will, for the most part, kind of skip through this because we can go through it at the end if we need to. Let's get to a nice picture there. Thank you, Nick. All righty, cool. So next up in topic 3 is topic 3b, which is Ampere's law, right? So that's this sucker right here, right? Don't worry about this part right here. That is referred to as the displacement current, and we touch on that in Unit 4. So don't worry about that part at all yet. But it basically says that this left-hand side here, right, this closed line integral of B dot dl is equal to this constant mu naught times the current through our Amperian loop, right? So we begin these Ampere's law problems pretty much the exact same way we would begin a Gauss's law problem, right? If I were to draw just a simple coax cable here, right, and I would say that I had current going through this center here, or not current going through here, I would have current going through something like that, right? And I would draw my Amperian loop similar to, like I said, how we would draw Gaussian surfaces, right? Somewhere in between 2 radii. All right. Hopefully those problems look somewhat familiar, right? The problem solving process is the exact same as Gauss's law. And the great news is that we can make these exact same symmetry arguments that we would in Gauss's law, right? So remember, that for Ampere's law and Gauss's law, we never really like to take that integral, right? In fact, we can't just straight up take it, right? So those symmetry arguments still apply. So that first one, I'll remind you, is that our B field vectors and our DL vectors have to be parallel to one another, right, to cancel out that dot product. Or if they're at some angle, multiplying by cosine or sine, depending on the orientation of your your Amperian loop, right? Some way to make them parallel, right? But if they are not parallel, in fact, if they're completely perpendicular, then we can't use Ampere's law. But most of these problems, we don't try to trick you to do anything like that. So for the most part, they will either be parallel to start, or they will be given at some angle. So you'll be able to reduce this to the integral of BDL. Right, and from here, most people remember this one is if we have a symmetrical shape, so things like cylinders, things like spheres, things like that. B field, if it is constant throughout my entire shape, or along the path of my Amperian loop in this case, right, I can pull it out of the integral and then end up with B times the path integral, or the line integral, excuse me, of DL, right, and I will just end up with B times L there. Right. If this is the free response question, and if there is a free response question, we will be usually look for justifications as to how you got from here to here, right? So it's pretty clear to people that you can get from one to the other, right? And in fact, most of you will just assume that. But if by chance it is the free response question, we will be looking for some sort of explanation as to why you can do that, right? So you'll be going through these steps, right? So B is parallel to DL, right? Then B field is constant everywhere along the length of my loop. That way I can get to just B times L over here, right? So we'll be looking for that problem solving process, again, if it is the free response question. If it's not, well then great, you can just prove it to yourself, right? So no big deal there. So moving on just a bit, in Gauss's law, right, I'll write that out up here, right? And we ended up with the surface integral, E dot dA equals closed over epsilon naught. Right, so that was Gauss's law. Right, I will say that in Gauss's law, if you guys remember, pretty much the only integral we had to take was to find our charge enclosed. Right, that was the bulk of the work of the problem. Right, because we made our symmetry arguments over here and ended up with the same sort of E times A relationship over there. Right, so Ampere's law is no different. Right, we can simplify this line integral of B dot dL just to get B times L. So that way, really, all we have to figure out is this current through term here, right there. All right, that is the magnetics, or I would say the Amperian law equivalent of charge enclosed, really. That's where most of the bulk of our work comes into play. So with that being said, the way we would take that integral is very, very similar to how we would find our charge enclosed, right? Where in our charge enclosed, we had the integral of some charge density, rho, for example, right? And then times some differential shape, right? So in this case, it'd be a three-dimensional shape, but you could obviously have sigma dA, or lambda dL, right? Either one of those three. Current is kind of nice because we only have one relationship to work with here. We only have this integral of J dA, right, which is the current density dotted with the differential area vector. Right, so it makes things, I guess, somewhat easier on you guys, right? We only have one form of the equation to worry about, right? But that doesn't make the integral any easier to take necessarily, right? So we can make those same arguments to start, right, where these two vectors are parallel, so I can get rid of the dot product and end up with just J dA there, right? But J, like I said before, is our current density, right? So that would be current over the area that it flows through, right? So this can look different for different types of wires, right? So if I just had, if I just had a wire with current flowing through the center, right, let's say that radius was A and the outer one was B, for example, right? And I just had empty space here between them, right? Just nothing there, right? The formula for my current density, right, J, would just be, we can just call it I total is what's flowing through here, right? So IT is just going to be equal to IT over, again, that area that it flows through, which would be pi times little a squared, right? There is no current flowing through this purple region there, right? So I can't do pi b squared minus a squared, right? Because that wouldn't make any sense, right? And I can't do pi b squared because that would include the empty space again. So it's very important when you figure out what your J is, right? If it's not given to you as a function, you figure out, okay, well, I have a total current here, right? And I have to find the total area that only the current flows through. right? Not the total area of my shape, just the total area that the current flows through, right? Very big difference between those two, because you'll get a incorrect answer if you try to use B there, right? Just for example, right? And then see this a lot. dA again has to be a differential. It has to be a differential area, right? So here you shouldn't see any. We shouldn't see for dA pi a squared here, right? Because that would be a definitive area, right? At least in this example, right? There's caveats, right? But for this example, if we're going to integrate from the center outward to find what our current through was, right? dA, it makes no sense to call that pi a squared because it has to include some sort of differential variable there, right? So that being said, right, just make sure, like I said, just make sure your dA and your area terms are not the same because they shouldn't cancel out in most examples, right? And some of them they will, right? And if it'll be pretty obvious. It'll just say, hey, the total current is this, and you're trying to find the B field at the radius, it's at radius A, for example, right? Then you wouldn't have to integrate. But for the most part, you will, similar to charge enclosed for Gauss's law. So I believe that covers at least the mathematical part of Ampere's law pretty well. Does anybody have any questions on that before I move on to just a quick picture example? Cool. Take that as a no. All right. And I'm sorry, by the way, for those of you that keep joining, feel free to ask questions in the chat. I see some of you already have, but Kate is going through and answering that, or answering those. So no big deal there if I go over something.
There seems to be a few specific ones concerning the example that you just did.
Oh, okay.
Like, why is area in J just pi times a squared?
Okay.
Like that.
Gotcha. Yeah, Eric. Okay, sorry about that. I didn't even have chat open. That was weird. So why is the area in J just pi a squared? So that's a good question. So that goes back to just this quick example that I drew right here. Right, I'm just saying that my current flows through this inner circle here. Right, so this inner circle has all my current flowing through it. Right, there's nothing but empty space in that purple area. Right, so current density J describes the total current, right, over the total area that it flows through. Right, so in this case, I just said some variable IT, right, for total current over again that area that it flows through, right, which is just pi a squared. Does that make sense? Yes, no. Okay, unless there's no objections, I'll assume that that took care of it. So Megan asks, so what is dA in this case? Well, that is a good question. So dA, we can think about this in a couple different ways. I guess the first way that I would think about would be just to find the area that we're dealing with, right, and take a derivative, right? That would be a mathematical approach to it, right? I'm not quite sure if Nick has a more conceptual way of going about it because he's a phys major and I'm not, but I like to go the math approach and just say, oh, well, my dA I know is going to be, or my area is going to be a circle, right, to start. If I start at this center portion here, right, that blue dot, and I move out from the center, right, at some radius r, right, but then I have to take the derivative of that, right, so this would be 2 pi r dr, right, for this hypothetical example, right, but the general rule of okay, well, finding an area and then taking a derivative of that is acceptable, right? But just to let you know, this right here is just specific to this example, right? So don't take that at like it's everything. But Megan, does that answer your question? Okay. Nobody's feeling very talkative now. Okay, cool. I'll assume that does answer your question unless we have any more objections. So please feel free to keep asking if you got questions, all right? Okay, cool, I see. So the R value will be where the current is flowing. Another good question. So the R value represents where okay, if we're saying to find the B field at some radius R less than A, right, we would draw our Amperian loop at that radius, right? So it would be, for example, over here, right, in this circle, right, my Amperian loop would be like that, for example, right, that blue dotted line, right? So that would be at radius R, right? Sorry, it's kind of hard to see there, right? So that R value would be how much of the total current that we have at that radius, right? Because that circle is my I can't write very much. Amperian loop. Right. So we're not necessarily saying that the R value is where the current is flowing. Necessarily. We're saying that at this radius R, I have some fraction of the total current, and I need to know what that is to actually find my B field, right? Because that would be I through right there. Sorry, it takes a second to dig. Yeah. So does that answer your question, Megan? Cool. Okay. Awesome. Thank you for responding. I appreciate that. So I'll just sit here in silence for 10 seconds. Thank you. All right. So any other questions about Ampere's law from a mathematical standpoint? Cool. All righty. So, okay, cool. Never mind. So Brett's got one. So the area in the current density is the total area with current, and the R on the dA is the radius of the Amperian loop. Yes, I'll say that. That sounds right. Yes. So the area in this current density. Whoops, that's an eraser. In this current density right here is the total area that the current flows through. Right. This is allowed to be a constant. Right. In fact, that it should be a constant. Right. For most problems. Like I said, in this case, we're saying all our current flows through radius a. Right. So it would be over pi a squared. And the R and the dA, right, is the radius of the Amperian loop. But remember, we can't just plug it in, right? We have to integrate from the center of my circle or the center of my wire to wherever I'm drawing my Amperian loop, right? So R as a constant is the radius of the Amperian loop, but in this case, it's variable, right? It's dr, right? R of dr. Does that answer your question, Rhett? Awesome. Cool. All righty. So looks like you guys have asked most of your questions, so I will move on to just kind of I guess a more pictorial reference.
Actually, I have a quick question for you.
Yeah, go ahead.
Yeah, so when you said that the A, so in J is equal to I over A, you say that A is usually always constant. Is that what you just said?
Yep.
Okay, so then when we take the differential of a constant, isn't that value just going to be 0 for the dA portion of that?
That's a good question. So remember that A and dA aren't necessarily related, right? And they can be in some problems, but in this case, they wouldn't be, right? Because that's saying that I have this would have to be some sort of non-uniform current density, or well, no, not necessarily. So this A right here is a constant, right? It's where this current is flowing, right? It's this red circle right here that I'm kind of highlighting, right, in blue, right? That's where all my current is flowing. The dA describes the differential area of my Amperian loop there, right? So it's the differential area of the circle that I drew at the radius r, right? So I'm not just going to take the derivative of pi a squared, right? Because I'm not at radius a, I'm at radius r, right? So it has to be differential, right?
Okay, that makes sense. Thank you.
Does that make sense? Cool. Just checking. Yeah, and so problems occasionally will switch it up and give you a function for J, for example, right? If that's the case, then you just worry about finding dA there, right? If they give you J, then you don't have to worry about any of this stuff right here, all right? Because it's given to you as a relationship. All right. Cool. Lots of questions about Ampere's law. That's good. That would be my bet for a free response question if we even have one, but we'll see. So make of that what you will. All right, so lots of good questions. Anything else before I move on from the math here? Cool. All righty. So next slide here is just a pictorial reference of kind of what the B field looks like around a current carrying wire. I will say that Nick was very proud of this picture, and I am too. It looks very, very nice. So it can be kind of hard to read though. So we'll take it apart here in red. Right, so this black line here, right there, I don't know if it's kind of hard to see. That's the current, right? That is our current carrying wire. And I don't know if it's hard to tell, but those arrows are kind of coming out of the page at us right there. So that means our current would be kind of out like that, right? So this is just, like I said, this is a great picture of just showing what the B field looks like around any current carrying wire. In this case, like I said, a closed loop, right? So if just real quick while we can introduce this, I have a couple of different right-hand rules that I use for figuring out B field direction. So you guys had a couple greater group activities that were asking about, B field directions and things like that. As far as this example goes, I would stick my thumb out of the page, right? So kind of towards me where the current's going. And then my fingers would curl in the direction of this magnetic field, right? So you see this counterclockwise trend here, right? So again, thumb towards me, it's kind of hard to see, but thumb towards me, right? That curls around in a counterclockwise direction, right? That's the one I have for just finding out which direction the B field is going if for a current carrying wire, right? If I were to draw this looking at it from the side, whoops, why am I trying to type? That's not good. If I were to look at this wire from the side here, right? Let's say this was my current carrying wire, right? I could do the exact same thing, right? My B field would be into the page on the top and out of the page on the bottom, right? Again, just doing the curl. Alrighty. So that looks pretty good to me. Like very, very nice picture reference there. All right. I think, yeah, I think that's it for Ampere's law. Anybody have any questions about that? Sorry, I'm just looking over the rest of these to see if I missed anything. No, not quite. Cool. Yeah, anybody have any last minute questions about Ampere's law before I move on? Ben, I see you raised your hand. Does that mean you have a question, or you're good to move on? I'm not quite sure.
By the way, Pat Cole just sent an email saying there would be a free response.
Cool. Thank you very much for letting us know, Dawson. Yeah. So yeah, exactly. So no changes, right? It should just be a normal exam, but except it's online. So thank you. All good, Ben. No worries. Just want to check and make sure. Yeah. So don't count the free response question out because there will be one. So it very well could be an Ampere's law question. It also very well could be a Biot-Savart law question. I've seen both. Faraday's law is a little less common. But obviously I would study those problems, but it is a little less common than I would say Ampere's law and the Biot-Savart law. So just keep that in mind. Don't forget about the free response question. Should be good. Thank you again, Dawson. I appreciate it. All right. So let's see. I don't think I missed anything, right? Again, just talking about those symmetry arguments, right? We should be able to, if you're asked, you should be able to show how you got from B dot dl to just B times L. Right? You should be able to show that and explain to us either in words or I guess typing it out, whatever way you want to do it. You should be able to explain to us how you did those symmetry arguments and got to this point, right? So if you have any questions about those, please speak up and ask. Right? They're pretty straightforward arguments once you learn them in the first place, right? But don't forget that we have to get rid of the dot product first, and then we can pull B out of the integral, right? Not the other way around. I saw quite a few people trying to do that in Unit 1. So with that being said, that pretty much covers Ampere's law from a conceptual standpoint. We can, like I said, we can go through an example at the end if that's what the popular vote is. But any last minute questions again on Ampere's law, or am I okay to move on to magnetic forces? Cool. All right, I will take that as a resounding move on. Alrighty, so like I said, just going to skip over this example, right? We'll go over it if people want to see Ampere's law. Right, worked out very, very nicely, thanks to Nick, so appreciate that. All right. Alrighty, magnetic flux. Yeah. Nick, I think I'll let you talk more about magnetic flux when you get to Faraday's law, because it's probably the place where it applies the best. Did you have anything in mind for talking about this slide specifically here?
No, that was just the thing we touched on super quick when we didn't have lecture, but we had studio, how there's fluxes through open surfaces, but if you have a closed surface, then there's never any magnetic flux. That's probably not going to be a test question, just keep that in mind.
I would be shocked if it was, I'll say that. So, okay, cool. I will let you introduce that in Faraday's law then. Sorry.
Sounds
Thank
good.
you for clarifying that. Move on just a little bit here. Alrighty, so another big part of Unit 3, right, and I guess Phys 2 in general, is the idea that these quantities that we work with in Physics 2, right, so magnetic fields, electric fields, things like that, they can be equated to forces that we've already worked with, right? So popular examples include, centripetal forces or just generic MA, right? Things like that, right? Always a huge part of physics is realizing that we can equate forces to one another, right? So remember that we learned two forms of the magnetic force, right? So one of them is not listed here. I will write that out. IDL cross B, right? One form, right? And the other form is listed right here, QV cross B, right? So both are equally viable. Sorry, I should say DF there. My bad. I would say that situations Go ahead. Sorry about that.
Sorry. It's DF, right? For IDL.
Yes, I apologize. Yeah, it should be different. It's differential by nature, but if you have a constant length, for example, then it would just be, ILB, right? For example, right? That's very specific, but that is the definition. I apologize for forgetting that DF there, but it is DF. Cool. Okay. So again, forms of the magnetic force, right? I think it's fairly straightforward to decide which one to use in which type of space. Usually for QB cross B here, they will tell you that an electron is moving through a magnetic field, something like that, or that just disappeared for whatever reason. Sorry. Don't know what happened there. Ugh. All right, straight back to it. Maybe. Cool. Okay. Sorry about that. Not quite sure what happened there. But so as I was saying, we have two different equations for this magnetic force here, right? It is, like I said, I think it's fairly straightforward to decide which situation to use which in. Right? I would say QB cross B is useful for electrons in magnetic fields, things like that. Or it'll just say like some generic like charged particle, for example. Things like that are more likely to be QB cross B here. All right. If I have, let's say, a current carrying wire, right? So I think you guys had one. This is kind of getting more into torque, but I had just a slanted wire. That's an awful picture. If I just had some slanted wire and I wanted to find, oh, sorry, I remember. You guys had on a homework problem, I believe, you had a force on like a cosine curve or a sine curve or something like that. Then you would have this is where you would use IDL cross B, right? Because you're usually given some function for current or some function for B field thing, something like that, and you can integrate to find the total force, right? So two different situations to use both these forces, right? Both useful in their respective places, but two very distinct formulas, right? So we can't use QB cross B for IDL cross B. Try to put it. All right. So that is the formulaic introduction, right? We got a couple slides here on using the right-hand rule, which are fantastic. So we can kind of go through these. So like I said before, me personally, I use two right-hand rules. I use basically what I call the three-finger one for this QB cross B, and then I use just the curl for just finding the direction of the B field in the first place. So what I mean by the three-finger one is the fact that, oh, hey, there's three fingers here, right? That's all I mean. So if I were to just to draw out a rough example here, right? Let's say we'll draw it in purple. Let's say I had a B field going into the page, right? And let's say my velocity vector was, let's see, what's the easiest way to do this on my hand? Up. That's up. Yeah. All right. So we'll make B into the page, right? We'll make our velocity vector up, right? And now we want to know what's the direction of my force, right? So I will set up my right-hand rule. Right? I like to go, B field is middle finger, so B for biggest finger, right, would go into the page, right? My V, my velocity vector, is my index finger, right? So that's going to point straight up, right? And that way my thumb will point in the direction of the magnetic force, right? So in this case, it would be left on the page, right? Again, just doing that right-hand rule, right? So where index finger points straight up for velocity, B field, biggest finger going into the page, and that way thumb will point straight to the left, or at least the left for me. One thing I will remind you guys to keep track of is electrons have a minus Q fundamental charge, right? So if, for example, this was an electron, so I'll say if E minus, then force is now going to be the opposite direction, right? So I like to do this where I just keep the right-hand rule normal at first, right? So I would normally say that, oh, well, my force would normally go to the left, right? But since it's an electron, I just grab my thumb and rotate it 180 degrees, right? Exact opposite of what a proton or what a positively charged particle would be, right? So if E minus, then that way my force is to the right, right? Allison asked a good question. So does a circle with an X through it always mean out of the page? A circle with an X through it actually means into the page, right? Think about it in terms of an arrow. Right, so if you're looking at an arrow imagine like an old style like Native American arrow, right? If you look at this arrow from behind, if you were over here, you would see just an X, right? You would see an X from there, right? If you were looking at it head on, you would see just a dot, right? You'd see just the actual tip of the arrowhead coming towards you, right? So very good question. I will say that this is, oops, that is out, right? And this is in. All right. That answer your question there, Allison?
Yes.
Excellent. Thank you very much. So Ryan says he's more fond of the curl right-hand rule. Excellent. That's the curl right-hand rule absolutely works in all cases, right? If that works for you, 100% go ahead and do it. I was never able to get the hang of it back in high school and here for whatever reason, so not quite sure. But the curl definitely does work for everything. I just like to do the 3-finger and the curl for different things, right? But totally up to you, right? I was just giving an example about just based on the 3-finger thing. All right. So you're more than welcome to use whatever one you want. Just make sure. You guys will laugh, but be sure use your right hand. Please do not use your left hand. That is, it's honestly kind of funny to see in studio, but when it happens on an exam, it just feels bad. So make sure especially if you're right-handed, right, make sure to put down your pencil and do the right-hand rule, right? Don't use your left hand. So again, you might laugh, but it's step one, right? Use the actual correct hand. Other than that, again, that kind of describes it from a conceptual level. So I will go on to, Nick actually had a great example here for me as well. He has the velocity going to the right in this example right here, right? But notice the force is still the exactly what we expect, right? So B, biggest finger into the page there, right? Velocity vector, index finger to the right. That way force would point up on the page, right? Again, this is assuming that it is a positive or just charge Q, right? If it doesn't say electron or charge like negative Q, for example, then assume a positive charge, right? Unless it says otherwise. So yeah, so these are great things to just test your knowledge on as well. You can also look up on Google just right-hand rule, right? And those should be some great examples there as well, right? Just to make sure you know which direction the force actually points based on which particle, all that good stuff, right? So that's great there. All right. Next slide, we have just a great representation of kind of what this force actually ends up looking like. So by nature, so the force exerted by a magnetic field on the particle that we were just talking about up here, right, is going to be of a centripetal nature, right, meaning that it steers the particle in a circle, right. This particle is bent by this, or the path is bent by this magnetic field, right, to form, like I said, to form that circle there, right. So where these red vectors are our force, right, and the green vectors are our velocity, right. So important things to remember about things moving in a circle, right? We normally say that forces are balanced, right? So you'd say that in this case, for example, FB equals FC, right? So magnetic force equals our centripetal force in this case, right? So M V squared over R, right? Just some helpful relationships if you're given problems similar to that, right? That is just a hypothetical thing, right? But keep in mind that for particles moving in a circle, right? And so yeah, so that's what's interesting about the magnetic force, right? It's not just like a straight up like friction force, for example, right, where it's always one direction, right? Magnetic forces are unique in the sense that they bend particles into circles, right? Which I think is pretty cool, but you guys probably hate it, so no worries there. The last thing we have to cover as far as magnetic force goes is when you will get a helical path versus a circular path. Right, and that was a question on the 3B studio, right? But I noticed that there was a lot of people that either didn't ask for help or were going about it the wrong way. So Nick did a great job here of writing out what it is from a conceptual standpoint. So if the way he has this written out, so if the velocity vector, right, is parallel to my magnetic field, right, then I won't have a magnetic force, right? That's done, right? Because magnetic force by nature is QV cross B, right? And a cross product is a measure of how perpendicular two vectors are, right? So if two vectors are parallel, then my cross product will be 0, right? So that's an easy one, right? If velocity is parallel to B field, entirely parallel, then you're good, right? You don't even need to do the right-hand rule because you won't have a force, right? But the more complicated example, right, is if picture's going to be kind of small over here, I apologize, right? If I have, for example, my velocity at a angle, here, right, some angle theta, right, from my y and x axis here, right? I said my B field, I believe in class, you guys, the example looked like that, right, where B field was to the right, right? And I was to describe this path, excuse me, this would follow a helical path, right? And so the way we can best prove that to you is that only the perpendicular components of my velocity to my B field are going to end up mattering as far as the circle goes, right? So for me to have a magnetic force, I have to have some component of velocity perpendicular to my B field, right? So that means that my parallel component here, right, this part along the x-axis here, will have no effect on my magnetic force, right? No effect at all, right? Meaning that if I were to just ignore it for a quick second and I just looked at the vertical component here, whoops, that's an eraser. If I just looked at the vertical component here, I would get that normal circle, right? Because I have some perpendicular component, right? But since this x component is unchanged, I would see that circle move in space, right? Creating a helix, right? The circle would be moving because this x component of my velocity here, right, in that red arrow there, is unchanged, right? It's a pretty important distinction. Does that make sense the way I'm drawing pictures and things like that, or is there still some questions on that? And just want to let you know, this is exactly what these paragraphs say. Exactly what the paragraph says is what I just said, right? Just trying to make sure that we get it in a words perspective. So if your charge only has one component of motion is a circle. So good question, Liz. If that component of motion is perpendicular to the B field, right, then yes, then it's strictly a circle, right? If your component of velocity was parallel to the B field, again, you'd be down here where whoops, right here where force is 0, right? Because it's a cross product, right? So I'm tempted to just say yes to your question all the time, right? Because if V is always perpendicular to B, then absolutely, right? Your force would be 0. Or sorry, if V is absolutely perpendicular to B, your force will be, QB cross B, right? If it's parallel, then you'll get no force at all. Does that make sense? Cool, excellent. And then Eric, yeah, you're right, exactly, right? So, yeah, that's, like I said, a pretty important distinction there. I would be shocked if you guys were given some question very specific to that, right? But very important to know, right, that this is a cross product here, right? And I really care about the perpendicular components, right? So keep that in mind. All right. Yeah, and this is just a great pictorial example of what that helix actually looks like, right? So notice what's common in all of these is this yellow/orange vector here, right? That is parallel to my B field, right? Notice how that never changes, right? It always points straight up, right? So meaning I will get this circle because I have some perpendicular component, that's the green one, right? But the circle will be moving in space, right? Because that component of velocity is unchanged, right? So again, just a great, like I said, I think it's a great pictorial example of what's going on here, right? But please speak up if that needs to be clarified anymore, because it is pretty important, but very, very easy to confuse. All right, looks like next. Cool, yeah. So the last slide I have to give here is just to summarize. So looking at this paragraph here, all right, so a charged particle moving in a magnetic field will travel in only a circular path if the velocity is perpendicular to the B field, right? So that is saying if V is strictly perpendicular to B, right, you will get a circle, right? Always, 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 always. If those two vectors are 100% perpendicular to each other, you will get a circle, right? This next paragraph talks about a charged particle in a helical trajectory if some components of its velocity is parallel to the B field, right, but not completely parallel, right? Very important. I'm going to highlight that, not completely parallel. This is saying that if my V total is equal to some parallel component plus some perpendicular component, right, then I will get a helix, right? Because remember, this parallel or this perpendicular component, right, creates my circle, right? And this parallel component is unchanged, right? So sorry, that's taking a second to upload or update. My parallel component is unchanged, meaning that the field does no work on that at all, right? It doesn't even touch it. So I still get that parallel path, right? Which back in this example was straight up, right? So that's why you see again that moving circle, right? And then last but not least, the best one in my opinion. So if the particle's velocity is completely parallel to the B field, right? So we're saying that V is entirely parallel, right, to B, right? Then I get nothing. No force, right? No force and no path, right? So no force, and I'll write up here no. Well, sorry, no new path, I should say, right? It says the particle, its trajectory won't change, right? I should probably erase that just so nobody writes that down. Yeah. So your path will be unchanged is what I should have said. I apologize. Eric, yeah, let me scroll up. Are you talking about this picture right there? Not sure how far. Right there. Okay, cool. Yee. Love that. All right. So that's I'm about to pass it off to Nick to talk about the rest of this unit. So that includes torque, Faraday's law, and something else that I can't remember. That's probably not good. But so he's going to talk about the rest of those. But before I go, does anybody have any last general questions about any of the topics that I discussed? Right. So that was the Biot-Savart law, that was Ampere's law, and that was introducing magnetic force. Right. Any questions about those at all? Right. We can revisit them later if you need to, but just so it's all fresh in everybody's mind. Any questions? Good stuff. All right, cool. Nick, I will stop sharing here. The floor is all yours. I will keep checking on that vote and look at some questions that we can possibly get going there. All right, it's all yours, man.
Awesome. Thank you. Give me a second to start sharing, and
Good.
I'll be. Cool. Yeah. So just as a reminder, these are already in the Teams channel, but if you download the HTML files and if you want to play with them so that your right hand doesn't get too strained, feel free to do that at any time. And the slides are here too. Cool. All right. One last concept about magnetic fields, and the first equation, the first force equation, is that one consequence of how magnetic fields behave on free charges is that magnetic fields never do any work on free charges. Because if magnetic force is given by QV cross B, and differential displacement has to point in the same direction as the particle's velocity, that just follows from the definition of what velocity is, well, then work, which is defined to be the integral of the dot product of f dot dl. Here's f, here's dl. One property of cross products is that cross products are always perpendicular to the two vectors that define them. So if this is my force right here, or yeah, if that's my force, the force is always perpendicular to my B field and my V. That means what I'm doing is I'm taking the dot product of two perpendicular vectors, and that is always 0. So that's just something to keep in mind. The most important consequence of that is that magnetic fields never change the speed. Obviously, they change the velocity of the particles. That's why you get things like a helix where it's moving in sort of a crazy velocity, but its net speed never changes, and hence its kinetic energy never changes. Cool. We have an example here that we can go through later. Okay, here's the other force equation that Tyler touched on. If we have current carrying wires, the differential amount of force dF on that current carrying wire is dF is equal to IL cross B, where dl is just an infinitesimal segment of that wire. It was brought up in the chat earlier, but it keeps coming up again and again in this unit. dl, just to keep in mind, is the differential vector that points in the direction of the wire. So for instance, if I have the XY plane and my wire is kind of looking like that, then my dl vector is just going to point along the wire. So it maybe points like there and there and there and so on. Cool. I have that slide twice for some reason, whatever. And here's a worked example that we can go through later. All right. The big topic that we hit in 3D was magnetic torque. Torque is where we have to go back to Phys 1. It's given by the cross product of r cross df, where r is the vector that points from the axis of rotation to the point where force is being applied. So for instance, I think there was a homework problem where we had the xy plane right here. Here's x, here's y. I think it was a straight wire segment, but we had a wire that pointed like that. And there was a force applied on that wire by virtue of a magnetic field pointing up on that page, and this wire carrying a current. And I can't remember how the wire was free to rotate. It might have been around the z-axis, it might have been about the x-axis, but regardless, the r vector is always just going to point from the axis rotation. Let's say it was rotating about the x-axis, so kind of like that. Which would mean that my r vector would need to point from the x-axis up to the point where force is being applied, and force is being applied on the wire. What ends up being more common though, is we have to use this differential form of that same equation. The differential torque d tau is equal to r cross df, because it's often the case that the force on this wire is non-uniform. Maybe there's less force here and more force over here, but it's usually the case that force is not uniform, so we have to look at this differential torque rather than the total torque. But we can still find the total torque by integrating the differential torque. And just like a linear force can be thought of as a push or a pull, a torque can be thought of a twist about some axis.
Nick, sorry, can I just input real quickly?
Please.
Yeah, just remember, guys, for example, this r vector is not the same as the one you would use in the Biot of law. Right? Nick's written it in paragraph form right there, but it is not the same. Right? The r vector for torque points from the axis of rotation to the point of where the force is applied. Right? In the Biot of law, we go from source to point. Right? So not the same. Right? Just make sure you know the difference between those two. Because if you use an r vector from source to point for a torque problem, you're gonna get the wrong answer, right? So just want to toss that in. Sorry, Nick, go ahead.
No, great point. Thank you. Yeah, if there's any more questions, feel free to interject at any time. I'll be happy to clarify. And here's another worked example that we can go through later. Cool. And now we have a generalization, or maybe not a generalization, but a special case of that torque equation. If we have some current carrying loop in a magnetic field, and only if we have a closed loop. So the loop has to be completely closed. We can't have a current carrying wire because that does not form a loop by itself. We need a loop closing in on itself. And we know what the number of turns is in that loop and the current in that loop. Then we can define the magnetic dipole, which is defined to be the number of turns times the current times the area vector. The area vector, or area vectors in general, they always behave like we've known them in Phys 2. If we have, say, this loop right here, the area vector is just going to point out of the loop. Sort of like that. It's not like, there we go. It points out of the loop or into the loop, just as long as it's normal to the surface that they describe. If that's the case, then we can say that the torque is just this magnetic dipole crossed with the B field. But remember, only apply this if we have some closed loop. If there's no questions, I can keep going. All right. Now we're getting into where, in my opinion, Phys 2 gets super exciting, and that's motional EMF, or maybe more generally than motional EMF, just electrodynamics, because pretty much what we've been doing in Phys 2 so far is pretty static. It obviously currents are moving charges, so that's the only place of motion where we've had so far, but we've been through electrostatics, we've been through circuits. Now we actually are going to observe effects where the effects that we observe are by nature of stuff moving. And that's where Phys 2 gets really exciting. Let's look at the first example. And that's a general category of problems that we call motional EMF problems. All right, let's suppose we have a conducting bar moving with velocity v in the presence of a B field, as shown. I think that one's, yeah, right here. So just so our right hands don't get too strained, it's moving that way out of the page, and the B field is pointing down. Cool. So it's a conducting rod, which means that there are charges in this rod, and those charges, by virtue of it being a conductor, are free to move. And if it's moving through, if the rod as a whole is moving through a magnetic field, then those charges are subject to the same magnetic force that we've seen so far in Phys 2. We've put our index finger in the direction of the velocity, and then our B field is going to be pointing down, which means that we have charges, positive charges being pushed to the far end of the rod, and negative, that leaves behind residual negative charges at the other end. Just to be completely formal, usually it's actually the negative charges that are doing the moving because it's electrons that are free to move in a conductor, but the principle holds either way. I think it's just easier to think about what happens to positive charges. Cool. So we have a magnetic force that's pushing charges to one end of the rod and leaving behind oppositely charged particles at the other end. What does that do? Well, whenever we have a separation of charges from positive charge to negative charge, there's going to be an electric field. So we have an electric field that's pointing along the rod from the positive charges to the negative charges. And in consequence, what happens is that, okay, well, there's a magnetic force that's pushing, let's say, the positive charges to the far end of that rod. But as soon as they start moving, there's an electric field. And what do positive charges do in the presence of an electric field? Well, they're subject to an electric force given by Q times E. Those same positive charges that were being pushed to the far end of the rod by the magnetic force, by virtue of getting separated from negative charges, there's now an electric field that's pulling them back towards the near side of the rod. So what happens is we get an equilibrium with equal and opposite electric and magnetic forces. Setting those two forces equal to each other, we have QV cross B is equal to Q times E. And as in this case, the velocity and the B field are completely perpendicular, so that cross product just turns into a simple multiplication. The Q's cancel, and we get E is equal to V times B. That relation comes up again and again, and we'll see it more in block 4, so super important. When we have this electric field from the positive charges to the negative charges that are now fixed in their spot because these two forces are in balance with each other, which means that nothing is going to move, or rather the charges are fixed in their spot once they got separated. So what happens is that more than just an electric field, we actually get a potential difference between the ends of the rod. And we can calculate this potential difference by integrating the E field along the rod. The E field we already argued is V times B, so just that integral comes out to VBL. Any questions about that? That's definitely, in my opinion, one of the most fundamental topics in block 3. Cool. Yeah, as always, feel free to interject if I'm going too slow or too fast, or something doesn't make sense, anything at all. Here's a worked example that we can go through later. All right. And now for the last topic that is examinable, because the exam covers through topics 3F, and 3F is Faraday's law part 2. So this is pretty much, once we get through here, we're done with the concepts review. Let's look at Faraday's law. Faraday's law, as it appears in its integral form on the equation sheet, is kind of scary. Definitely when I took Phys 2, I saw that and I got like, it definitely made me nervous to look at it because it's crazy integrals both on the left and the right, and then there's derivatives in there. So let's break it apart. Let's start with the right hand side. That quantity inside the differentiation, or rather what we're taking the derivative of with respect to time? Well, that's just a magnetic flux. Magnetic flux, as with electric flux, is the integral of B dot dA. Okay. All that we have to know here is that it's a flux over an open surface. We touched on this quickly before, but Faraday's law is only going to apply for open surfaces. So as long as we're taking the magnetic field times the area through an open surface, that's going to go as flux, and then we just take the time derivative of that quantity. That takes care of the right-hand side. For the left-hand side of Faraday's law, that's where it gets kind of most tricky. The left-hand side of Faraday's law is a closed line integral. So it's the closed line integral of this quantity, E plus B cross B dotted with dl, where this dl and the line integral, it's a line integral on the boundary of the loop through which we were considering the flux earlier. So maybe we have some open surface here, and we're considering the flux through that open surface. Then the left-hand side of Faraday's law, that's just going to be the line integral of this scary quantity on the boundary of that surface. So going along the boundary. All right.
Wait, so the left-hand side? Sorry, so the left-hand
Yeah.
side is like the boundary, and then the right-hand side is like the area in the middle kind of thing.
Absolutely.
Okay.
So most often how we apply Faraday's law in Phys 2 is for, where to go? Right here. It's for loops, usually. Like say we have a wire loop. Let's do brown. So if we have a wire loop and it has some number of turns, and let's say there's a changing B field through that wire loop. If there's a changing B field, then there's a changing flux in the middle of that wire loop. The left-hand side of Faraday's law is going to be the line integral along the boundary of that loop. And we'll see this further down, but what that line integral often comes down, or always comes down to, is just going to be the induced EMF along that loop. So it's going to be the voltage in the loop here.
Okay, thank you.
Yeah, of course. Yeah, great question. Let's look at each of the two terms in the left-hand side of Faraday's law. So that term, that first term, the closed line integral of E dot dl, if we were in electrostatics, that quantity would always be zero. Integrating the electric field over some closed loop would give us zero if this were statics. But what's different about dynamics is that if we have changing B fields, if we have time varying B fields, those produce what are known as curly electric fields. Another word that you might hear is non-conservative, which means that this quantity, the closed line integral of E dot dl, is no longer zero. And where that would come about physically is if we have like a stationary loop that's not changing, and we're wiggling a magnet, that's creating a time varying B field, which is in turn creating a curly E field. Taking the integral of that curly E field along the closed boundary of the loop gives us some voltage. We also have the right-hand, or the second term in the left-hand side of Faraday's law, which is the closed line integral of V cross B. This term says that motion of the loop itself also creates voltage. So maybe what if we held the magnet still, but we waved the loop around? That would also create a voltage. And what's interesting is that this integral of V crossed with B dot dl, notice it's super similar to what we saw before with motional EMF. If we go here, it was an integral of VB dl. It's a little bit different because Faraday's law is necessarily on a closed loop. So like we couldn't apply Faraday's law here because there's no closed loop that we could have considered. But that's just a thing to consider that. Let's go back. Here it is. The closed line integral of V cross B dot dl, that's a voltage that comes about by virtue of moving a loop with respect to a stationary B field, hence the velocity. Luckily for all of us, those are just sort of concepts that are good to keep in mind, but we don't have to deal with the left-hand side of Faraday's law at all in Phys 2. Because what's neat about Faraday's law is Faraday's law doesn't care whether the induced voltages come from time-varying B fields, which would be that term, or from stationary B fields but moving the loop. It doesn't matter where the induced voltages come from. As long as there's a changing flux, there's going to be an induced EMF. And that gives us the super nice, concise way that we deal with Faraday's law in Phys 2. We just say that the EMF, which is basically all the stuff on the left-hand side, is equal to the negative integral of, or sorry, the negative time derivative of the flux. Again, if the flux through area is changing for any reason, there's going to be an induced EMF on the boundary of that region. And that leads us into topic 3F, which is the last topic, Lenz's law. That sort of just addresses the minus sign in Faraday's law. Faraday's law is useful when we're solving problems to find the magnitude of voltages, because we can just say that the magnitude of the voltage change is the time derivative of the flux. But actually determining which way the induced currents go or the induced voltages go is sort of tricky. We can hypothetically do it with this left-hand side of Faraday's law, but that's scary. We don't really want to deal with that integral ever. So instead, we have this neat little law of nature known as Lenz's law. And Lenz's law asserts that when a thing is being induced by Faraday's law, the induced effects will act in such a way as to oppose the change that caused it. So not a problem, but let's look at an example real quick. Let's say we have a loop of coil. And let's say there's a B field pointing out of the loop. Okay, there's a B field going through a loop. That's not too exciting, it's just a flux right now. But let's say that B field is a function of time. And with time, that B field is getting bigger and bigger and bigger. It's going out of the page more and more and more. Lenz's law asserts that the induced effects from that changing flux, because there's now more B fields, so now there's going to be a different flux in that area. The induced effects need to counteract those changes. So the current that's going to be induced in the loop is either going to go clockwise or counterclockwise. I don't really know which way yet. But let's think about what's happening to the B field. It's getting more and more it's getting more and more upwards. It's getting stronger and stronger upwards with time. That means that the induced EMF, or sorry, the induced current has to necessarily be going clockwise. The reason being, if we consider the B fields that current loops by themselves create, if we just forget this whole example, for instance, and just look at a completely unrelated current loop in space that's creating, or that rather has a clockwise current, the B field from that current carrying loop is going to be pointing into the page if we use our right-hand rule. It's going to be pointing down or into the page, sort of from the perspective, which means that the induced B field created by this induced current is going down in opposition to the changes that caused it, which was this increasing B field up here. I think that's pretty much it for concepts review. If anyone has any questions, I'm more than happy to go back.
Well, looks like everybody's good there, Nick. So I
Awesome.
don't know if you saw it, but it seems like RC circuits, BOS-of-R law, and the magnetic torque are the problems people would like to see the most. So I think it's probably best if you take the torque one because you discussed the torque topics. But I wrote out a couple examples for RC circuits and for the BOS-of-R law. So
I also have I found typed examples for the RC circuits if you want me to send you those.
Oh, okay. Actually, I found a homework problem that I think is pretty good.
Sure.
But
Let's do that.
yeah, but let me know. All right, so yeah, I'll go through mine first. I'll give you some time to do torque to figure out an example for torque if you want. So cool. Okay, let me share my screen here again. Cool. All right, so like I said, just to reiterate, people want to see the RC circuits, Biot-Savart law, and magnetic torque. I will be covering RC circuits and the Biot-Savart law. I'll try to go through them reasonably quickly, just so we have time for Q&A at the end if people want. Right, but if I'm going too fast, please let me know and I will slow down. For reference, the problem I chose for RC circuits was the switching on problem, which can be found in homework 2E. Right, it is the second problem in that homework assignment. So if you guys want to follow along, if not, I've provided everything here and we can work through it anyway. But just to let you know, that's what the problem we're working with is. All right, so yep, as usual, please ask questions in chat if you have any, or go ahead and unmute and ask them straight up if you'd like. But all right, we'll go ahead and get started. So in this circuit that we've drawn here, we've got a battery hooked up to a resistor and a capacitor, right? And there happens to be a switch in between points A and B right here, right there. Right, so the problem says that the switch started at A, right over here, right? It started at A, was there for a very, very long time, and then it switched to B at time, what we're calling time equals 0, right? So one thing that I found frustrating about physics when I was taking the class was that we use correct language, but it's not straightforward, right? So when we say things are there for a very long time, assume t equals infinity. Right, assuming that this battery has been hooked up for this or hooked up to this capacitor for infinite amount of time. All right, so with that in mind, we have to go back to exactly how capacitors behave in circuits, right? And it's been a long time, so feel free to ask questions. But just as a conceptual overview, right? So capacitors that are uncharged act like wires, right? They act as if they have no resistance or very little resistance, and current can flow through them freely, right? So nothing out of ordinary there. So what that means is that once the switch started at A, like immediately started at A, right, the voltage across the capacitor would be 0, right? It would be 0 because those things act like wires, right? And as soon as they're plugged into batteries, they start off as wires, right? And they'll get more and more charged as we go along. All right. So on the reverse side of that, capacitors that have been plugged in for a very long time, right, act as basically breaks in the circuit, right? So if you think about, if that's not easy to visualize, think about capacitors like buckets, right, and current like water, right? If I leave a hose in a bucket for a very, very long time, right, and I take the hose out, right, that bucket's going to be full, right, and I can't put any more water into that bucket, right? But conversely, like I said, as soon as I put the hose in the bucket to start off the whole process, it was empty to start, right? So I find that analogy usually works pretty well for figuring out what capacitors act like in terms of time, right? As far as a mathematical approach to this, you have a couple equations on your equation sheet that look something like this. Let me actually write them out how they look on your equation sheet so I don't get them wrong. So you have two of them in the circuit section that look like this. So they're under the section RC circuits, right? And they say this right here. So we have Q of t equals Q final. I'll just do QF, and then 1 minus E negative t over RC. Right, so there's one of them, and then directly to the right of that you have another one. It looks like this. Right, QT equals QI, right, times, whoops, I don't need there, E to the negative T over RC. All right, so hopefully you found those equations. They're just right there under the circuit section. So the good news is that these are the only two equations we have to work with as far as RC circuits goes. Well, I mean, beyond Ohm's law and things like that. And it might not become immediately obvious, right? But these equations correspond to either charging a capacitor or discharging a capacitor, right? Or a resistor, things like that, right? Just dependent on what modes of circuit elements you're dealing with, right? The first thing I want you guys to know is that just because these equations say Q here, right, doesn't mean that that's the only form of this equation. In fact, I can use any variable that can change with time. Right, so I can either use V, I, or Q. Right, so all of those are interchangeable. Right, meaning that I could have V of t here and V final right here if I really wanted to, or the same thing with current. Right, So don't think just because we're dealing with capacitors and batteries and things like that, that I'm only relegated to using this equation, right? Because I'm not, right? I can use any time varying element of circuit analysis, right? So V, I, or Q, right? Can't use R because R, for our intensive purposes, doesn't change with time. All right. So that's the first thing I want you guys to know. I can use voltage, current, or charge there, any one of the three. The second thing, we're going to cover exactly how we can figure out which one is a charging equation and which one is a discharging equation. Right. So I'll take this upper one here first, right? And I'll bring it down here. Right. So this one says Q of t equals QF times 1 minus E negative t over RC. So there might be different ways everybody likes to do this, right? But what I like to do to prove these equations to myself is just to plug in t equals 0 to these equations, right? And you can see what happens, right? Because I know that an uncharged capacitor acts like a wire, right? And I know that a charged capacitor acts like a break in the circuit, right? So by plugging in t equals 0, I can find the state my capacitor is in and use whichever equation corresponds to that, right? So for example, Q of 0 in this equation, right, will give me QF times 1 minus E to the 0 power, right? Anything to the 0 power is 1, right? So here in this parentheses, all I have is 1 minus 1, which obviously is 0. So meaning I get nothing here, right? So at time t equals 0, I have no charge in this case, meaning that this is the charging equation, right? So as my time increases, I will keep collecting charge on the surfaces of my capacitor plates. All right. Does that mini proof make sense? Is there any confusion with that, or does that seem pretty straightforward there? I'll consider it making sense if nobody says anything. So I guess I'll move on to the other one. So obviously by process of elimination, right, the other one must be a discharging equation. Right, we can prove that as well. Right, say QI E negative T over RC. Right, if I were to plug in t equals 0 right here, I would just get QI, right? Because e to the 0 is 1. All right, so this is my discharging equation because I'm assuming that at time t equals 0, my capacitor is full, right? It has the total amount of charge on it, right? So that means that any t I plug in that's greater than 0 will experience a decrease in charge or voltage or current or whatever it is, right? So one is for charging, one is for discharging, right? Very, very important to know the difference between those two, right? Especially on an exam. I don't know what the problem is necessarily going to look like because we haven't done it to where these problems have been split up between exams, but that kind of covers exactly when to use those equations. All right, so before I move on to the actual problem at hand here, does anybody have any questions on how these two equations work, how to tell the difference between the two, anything about that from a conceptual standpoint?
I just have a general question. It doesn't have to do with this. Is there AC on this exam?
Yeah, so 2E and 2F, 2E is RC circuits and 2F is AC circuits. AC doesn't have much meat to it, really. You really just need to know reactance, impedance, and to me that seems like that's it, reactance and impedance. And I can do that really, really briefly after I finish this example. There's like 2 equations you need to know. It's pretty straightforward.
Yeah, thank you.
And
Yeah, no
RMS power. Or sorry, RMS current and voltage.
Yeah, that's
Yeah.
a good point.
Yeah.
Thank you. Yeah, sure. Okay, cool. So I'll assume that from then on, we're ready to actually move on to the problem, right? So the first part of the problem says, let me check, just make sure I get the wording right. It says so suppose we got a bunch of values here, right? We want to know what the voltage drop across the resistor at some time would be, right? So if I go back to my circuit here, right, it says that my switch is now at B, right? So I'll draw a little arrow there, right? Meaning that my capacitor now acts like my battery, right? It's supplying the voltage to the rest of my circuit, right? So my current is either going, it doesn't really matter, but either clockwise or counterclockwise, right? Meaning that I only have things going through the resistor and the capacitor. All right, so if I move the switch to point B, right, and my capacitor is full, that means I must have to use the discharging equation to find out the voltage of that resistor, right? Does that seem to make sense? Right, because my capacitor started off full, and every second that goes by, I'm going to lose some voltage to my resistor, right? If it helps, think about the resistor like a light bulb, right? And I remember doing these experiments in studio, right? We just had a capacitor hooked up to a light bulb, and you guys would discharge it through the light bulb and watch the light bulb, get dimmer and dimmer as time goes on, right? Exact same thing we're doing here. So this first part says find the voltage after a certain time. Well, all I'm going to do is say voltage at time. In my case, it gives me 2.5 milliseconds, right? So it's going to be 0.0025, right, seconds, right? And I would just do the voltage across the battery, right, because that's the total voltage in my circuit, times e to the minus t over RC, right? Or RC is that time constant, right? Otherwise known as tau, right? And it's calculated just by multiplying R and C together, right? No trickery there. It's just RC. All right. So I think that one is fairly straightforward, right? It's pretty standard. Just, hey, can you use this equation? All right. So the next one, I don't think is a super good thing to go over because it's just talking about power, where it normally doesn't, or which it doesn't use these equations directly. So I'm going to skip that part for now because it doesn't use these equations directly, and then go to the very end part. So the last part says that the switch has been at position B for a long time now, right? So it's been right here for almost infinite time, right? Meaning that my capacitor has completely discharged through my resistor, right? The voltage is 0 now, right? So now I'm going to, I'm going to switch the switch around, right? And have it go back up here. So the capacitor gets charged again, right? So obviously I gave it away, but if our capacitor is started off empty, right? And then I move the switch to connect to the battery over here, my capacitor is going to slowly charge, right? Meaning that if I want to find the voltage drop across the capacitor after a certain amount of time, I need the discharging equation. So the other one, the charging equation, that's my bad. Just spoken correctly, right? So the charging equation is B times 1 minus E negative T over RC, right? And fundamentally, it's the exact same problem-solving process, right? I plug in what I know about VB, right? It's just the given voltage in the problem, right? And then I plug in what I have for R and C over here, right? The time constant, right? If I calculate both of those, they'll give me, some number, right? And that corresponds to both of those answers, right? So RC circuits, I would say that there isn't much to get really confused here, basically beyond these two equations. So because these are the only two equations we have to work with, right? So if we can identify what these equations are on the equation sheet first of all, right, and then plug in a time and figure out for ourselves which one's charging and which one's discharging, right? Then we're good to go, right? These problems are easy money, right? You see one in the exam, you're like, oh, great, right? I have one equation to plug this into, and I'm good to go. All right. That pretty much covers RC circuits. Briefly, I'll talk about our 2F, which is AC circuits. In AC circuits, we had just a couple of things we wanted you guys to know. First of all, there's a couple of equations on your equation sheet to work with in this unit. So I guess what I'll start off by saying is that if we wanted to figure out the resistance of an RC circuit, right? If I wanted to find the total resistance of this circuit, for example, right? I couldn't just add R and C in series like I normally would add resistors for, right? Capacitors don't work like that, right? They have their own special resistance based on some other factors, right? And in fact, we call the resistance of a capacitor, we call it reactance, right? So on your equation sheet, reactance, it doesn't say exactly what it is, or I mean, it doesn't say that it's reactance, but it gives the formula, is equal to X. I call this variable X sub C, right, for capacitor, all right? And that is equal to 1 over omega C, right? So 1 over the angular velocity of the sine wave that goes through the capacitor times the capacitance of the capacitor, right? I will say really quickly, more often than not, we give you guys a frequency instead of a angular velocity. So really, this is just equal to 1 over 2 pi f c, right? Where omega is equal to 2 pi f, right? Just a quick phys 1 conversion there. All right. So now that I've got reactance out of the way, right? Once I have this, I can now solve for what we call the impedance of a circuit, right? Which is, you can think about that as an equivalent resistance based on if there are capacitors or resistors in there together, right? And that is given by a variable we call Z, right? Impedance, right? And let me make sure I write down the formula exactly how it looks, right? Just so there's no confusion there. All right, it says right next to it. So Z is the square root of R squared plus XC squared, right? So it's taking a square root of the sum of the squares of the reactance, which I would have just calculated, plus the resistance, right? The resistance, we don't need to do anything fancy with that, right? We just have to make sure that if there's more than one resistor in the circuit, right, we take that, this is the total resistance of the resistors in the circuit, right? Not just one, for example, right? So that's important to remember. If we have more than one resistor, this is technically RT, our total of the resistors in the circuit, all right? So other than that, oh yeah, the RMS stuff. So Nick, correct me if I'm wrong, but all I have for RMS is that it's equal to yeah. So I have some, like, let's take current, for example. I have I RMS, right, is equal to the max current, right? So the total over the ratio square root 2. That's literally all I have written down for RMS. And really the definition of it is that it's referred to as the root mean square. And if you think about it, it's really just the average of a wave, right? So if I drew myself a rather shitty looking sine wave there, right? If I took the average of this function, I would get 0, right? Just the straight up average, I would get 0. Right? So obviously that doesn't help us, right? To say the average of a sine function is 0 means literally nothing to me. Right? So instead, root mean square was created such that I'd find the value that it hangs out most often, right? So really, it's about 0.707, something around there, right? And that's what that means. And it's found by taking the peak value, right? So in this case, it'd be I max, right? And then dividing it by the square root of 2, and you'll get some value just kind of in here, right? Because if you'll notice, this is where plus and minus, this is where this function spends a lot of its time, right? So all the way over here, just a quick picture representation of what that actually means, right? So, but other than that, this is all I have for the actual calculation of it, right? It's just the maximum divided by the square root of 2, just a ratio. And I guess the last thing I'll say about that is we did this in our RC filters lab, right, where you guys actually had the function generator and things like that, and you had to find the breakpoint frequency, right? You did that by using basically a root mean square relationship, right? Just an FYI.
Yeah,
all right.
That's dead on. If I can just add to that, that's dead on. And then the reason why that's important is, or where that comes into play when you're doing calculations is if you have AC circuits, you have a new version, so to speak, of Ohm's law, which asserts that V is equal to, instead of IR, it's now I times Z, where RMS V, yeah, where you're using RMS current and RMS
Exactly.
voltage.
Absolutely, yes. Thank you, Nick. I totally forgot about that. That's the last place where this applies. All right, thank you very much. Yeah. So anytime we have a AC circuit with currents with capacitors and resistors, right? We have a new version of Ohm's law, right? Which is theoretically still V equals IR, right? It's a current times a resistance, but now this R changed to an impedance, right? Our total resistance, making sure we take everything into account, right? That's fantastic. That's all I have for RC and AC circuits, though. Any questions about those before I move on to the Biot-Savart law? Cool. Looks like we're good to go there. Yeah, those problems are fairly. Go ahead.
I can take Biot-Savart law if you want to break, since you've been you got up.
All good. I'm not prepared for a torque problem, so I was thinking I'd just do this and let you take care of torque.
Sure, I can do either one.
Cool, excellent. I won't do a ton of, well, actually, no, that's fine. That's fine. All right, so before I get started here, just let you guys know, this is the B field of an exponential wire problem from Studio 3A. Right, this should look pretty familiar because we've done the problem about 2 or 3 times now. Right, you guys had it as a graded group activity, so it wouldn't surprise me if it came up again. Right, but just let you know, this should be fairly familiar. So this problem in the actual studio is a scaffolded problem. Right, it's asking everything step by step, which is good because that's probably the way that a free response question would go. All right, so just kind of working through this example, right? 3A on Studio 3A. The first question asks, what's the direction of the B field in this region, right? The region in the wire, right? That blue region there. Right, so if I do I do the curl right hand rule for this one, right? So I'll point my thumb in the direction of the current and curl my fingers in the direction of the B field, right? Meaning that my B field will be out of the page here and into the page on the bottom, right? Or B field is in the minus k hat direction. All right, so that's step one, right? Figuring out what the direction of our B field even is. All right, good stuff. Next step is to actually write out the BO sub R law. Right, so I'll say that dB equals mu naught I times dl cross R over 4 pi R cubed. All right, just writing out the BO sub R law. All right, and so like I was saying when I first touched on it from a conceptual standpoint, is these problems are nice in the sense that they're meant to be done scaffolding type of way, right? As in I can find my DL, then I can find my R, I can take the cross product of the two, and then plug in everything back into here, and then take my integral. Right, so there's a very clear-cut process to follow when doing these problems, right? You don't have to do everything all at once, and in fact, I wouldn't recommend it, right? Just take things step by step, right? So what the scaffolded problem says is to start with DL, so that's where I'll start. So DL, like Nick was saying earlier, is by definition the differential length vector, right? It will point anywhere along this current carrying wire here, right? It just goes along with the direction, right? And if this problem was the free response question, be prepared to label those vectors, right? So just letting you know. All right. So really, my differential length must describe. Sorry about that. Must describe the an infinitesimally small piece of this wire at any point along it, right? It's got to be differential. Okay. So as I stated earlier, I'm not a phys major, so I take things a little bit slower. What I like to do is start with a length vector first, and then take a derivative to find differential length. Right? If that doesn't work for you, you can just go straight to DL. Fantastic, that's great. Right? I found that starting with L and DL usually ends up with less mistakes. Right? So this is the way I'm going to go. So the length vector again just has to describe any point along my curve. Right? So if I looked at the I hat component first, right? All I'm doing is moving out in the x direction. Right? So from a variable standpoint, I can just say that's x. Right? Because all I'm doing is starting at the origin, right? And I'm moving along this function any point along it. Right, so this would be at distance x, right? This would also be distance x. It just depends on where you're actually at the length at. Okay. So length I have x I hat, right? And then now we have to worry about the y component, right? Which just describes the height of this function at any point in time or any point along a certain distance, right? And you'll notice that we are actually given a function for that current or that y height, right? So all I have to do is plug in that function there, that parentheses 1 minus e negative ax j hat. Right, so that's just my x component there on the I hat direction, and then my y component. Right, that's just how I would describe this function at any point along its trajectory or whatever. All right. Now the great thing about DL now is that since I've got L, I could just take my derivative, right, implicitly with respect to x. Right, meaning I won't say the derivative is 1, right, because it's a variable, right? So I'll do the same thing here, right? So I'm going to get so when you take the derivative of 1, obviously that's 0, right? I will take the derivative of exponential, right? You bring down that constant, right? So I have a e negative ax dx, right, for that. Right, again, just taking that implicit derivative. All right, any questions about DL? I find that's the place people usually make the most mistakes. Cool, sounds good. All right. So the next place I like to go after DL is just to find my R vector. Right, because it's the next thing I need to actually calculate that cross product. All right, so my R vector, by definition, is a vector that points from the source of my magnetic field or my current, right, to the the point that I'm trying to measure it at. right? So let's say, for example, I just took this blue point right here and I just said that's where I was going to measure, right? Or actually, why don't I start back here like I said it was going to. So at any point along my curve, my R vector points from the source of what's making my magnetic field to the point which experiences it, all right? So this vector has to describe how I get from this point here to point P over here, right? The way I like to do these is just to, start where we said our point was going to be, right? And then just move down and to the right from there, right? So that's my y component, and that's my x component, right? So the tricky part is that I have to figure out how to describe these distances in terms of things that I know, right? In terms of, in this case, in terms of x, right? Because I'm taking a derivative and taking an integral with respect to x here, right? So that being said, R vector, right? Let's look at the y component first. I think that was a little more straightforward, right? So, and no matter where I'm at along this curve, if I was here or here or here, right? That y distance is always going to be represented by this function here, right? Because it was given to me and it describes the value, the y value of my function anywhere at any x value, right? So that one I feel is pretty straightforward. Right? I'm just going to write that out again. And that's going to be plus 1 minus e negative ax j. Right? Oh, sorry. And then one last thing. We have to move down from, no matter where I'm at on my function. If I was up here, for example, I still have to move down to get to my point, right? So I almost messed it up. This needs to be the negative version of that function. Sorry about that, right? Because we are moving down to get to whatever point P is, right? Which is down on the x-axis. So I apologize for that. All right, the last thing we have to worry about is this I hat component here. All right, remember that I hat component has to describe this x right there, right? No matter where I'm at. So, right, how do I describe this distance? All right, the total distance I'm given as 4. Oops, that's a terrible line. Right, I'm given 4 there, right? And if I already came out a distance x in the in the x direction, right? The difference between the two, right, would be running out of places to write things. Right, that difference becomes 4 minus x. Right, the total distance minus the distance that I had to come out from my origin there. All right, does that make sense? I think having a picture really helps. If I could draw a line correctly. Cool. All right, sorry, I'm annoyed by crooked lines. So I will write in 4 minus x here. All right, and now I have my r vector. All right, I'm at this point, I have dl, I have r. All right, so I've got this entire first part of the numerator of my views of R law completely done. All right, the denominator is just plugging in the magnitude of r. I need to cube that, right? And then I would have to integrate to find my B field. Right, so I'm not going to work through how to do the cross product because it should be, you guys have been doing cross products a lot in Calc 2 and things like that, so we should be fairly certain on how to do those. I will talk about, I guess, just the bounds on this thing last, because that's it. That's all we have to do. Because this problem is all just asking you to write out the integral expression. All right, so it's going to be u naught I times whatever that cross product is. You have to go back and find it. It's not a big deal. Over 4 pi magnitude of that r vector cubed. All right. So the last thing I have to worry about is, like I said, the bounds on this integral right here. Right? I established that my integrand is, well, all of this stuff right here, right? And the variable that I'm integrating with respect to is x, right? Given the fact that I have a dx in my dl, right? And whenever I cross it with my r vector, I will still get a dx term in there somewhere, right? So if this integral is with respect to x, then my bounds also have to be with respect to x, right? And the point that I want to find my magnetic field at is at 4, 0, right? So my bounds will begin at the origin, right? Because that's where my function starts right here, right? And then I will go to 4 meters or for whatever it is in the x direction. And once I take that integral, that will be the B field. So pretty clear-cut problem-solving process, if you ask me. I think it's breaking it up is very nice, having DL and R and all that good stuff.
Wait,
Uh,
the R? Because like, don't you have to find like regular R? Do you just square root it? Do you have to find regular R or no?
We do have to find regular R, right? Because we need to find magnitude of my R vector cubed down here at the bottom, right? So after I have R,
Okay.
yeah, magnitude R vector is just, the square root of the sum of the squares of those components, right? So 4 minus x squared plus, it will be plus, but I'll just distribute the negative. 1 plus e squared. All right, so that would be the magnitude of my R vector, right? And I've just got to cube that once I finish it.
Okay, thank you.
Yeah, no problem. Any other questions about this Biot of R law problem? Cool. Well, like I said, the last thing I'll say is make sure, I would say if you're going to do a Biot of R law problem to study with, I would either do this one or the ring of charge that's posted in the notes. Either one of those is, I guess, is fair game for having a Biot of R law problem. I've seen this one on exam in the past, right? So this is the one I would study first, right? But other than that, if there's no further questions about Biot of R law, I'll pass it back to Nick to talk about the magnetic torque problem that he's chosen. So go ahead.
Thank you. Let me share my screen. All right, let's do the example that's in the slides that I posted. So that's on page 53, if you want to follow along. And let's zoom out a tiny bit. All right. So we have a wire carrying a current I, and it's free to rotate about the y-axis. Whoops, that's not what I meant to do. It's free to rotate, let's do it in orange, about this axis here. And there's a uniform magnetic field with magnitude B naught pointing in the j hat direction. We need to find the torque on this wire segment. All right, let's work out a strategy. We can first start by finding the differential amount of force with the equation that gives us differential forces on current carrying wires, dF equals IDL cross B. And then we can get the R vector, which, just to beat this drum one more time, it's different than the R vector in the Biot of R law. This is the R vector that points from the X rotation to the point of force application. And finally, we can integrate d tau, the differential torque, to find the total torque. All right. Let's proceed with finding the differential amount of force. So dF is equal to IDL cross B. That's from our equation sheet. And we have one of those vectors. We have the B field. It's just uniform and in the y direction. So B naught j hat. Let's now find the infinitesimal length. So if I draw my setup one more time, I have the x-axis here and then the y-axis. And my wire is just pointing, let's keep it gray. It's just pointing along there. It's at some angle theta. But regardless, DL describes some infinitesimal displacement along this current carrying wire. So maybe my DL vector, let's make it blue, is pointing along this current carrying wire. And to find what that DL vector is, we can partition it into its I hat component, which is dx right here, and its j hat component, which is dy pointing up. Cool. As what we did with the problem that Tyler just showed, we want everything in terms of x, because ultimately we're going to have to take an integral, so we need to express everything in terms of just one variable by itself. X is usually the choice we go with, so we'll leave dx by itself. That differential displacement in the x direction, we just leave it as dx. But now we need some way to figure out how to write dy, this one right here, in terms of dx, or in terms of x components. All right. Well, we know that this dl vector is pointing along this line. So what if we had an equation for that line? Let's do that. The slope of that line is just its rise over its run. So if I redraw it, and we'll keep it in gray, the amount it rises is right here. That's just L sine theta. Yeah, because theta is right here. So L sine theta is this side length right there. And the amount on the bottom, the run of the slope, is just L cosine theta. L cosine. I'm not going to write that because it's cramped there, but that's L cosine theta at the bottom. All right. So now that we know the slope of the line, and we know it starts at the origin, we can just say that the line itself, the equation that describes our line, is just the slope times x, y equals mx plus b. So y is equal to tangent of theta times x. Tangent of theta, this quantity right here, is a constant. Even though it has theta in it, theta isn't changing, so that's just some number. Okay. Now we're still trying to find dy. So now that we have y, we can take a derivative. If y is equal to tangent of x, tangent of theta times x, the derivative of that with respect to x, again, not with respect to theta, so it's not secant squared theta. The derivative with respect to x is just its slope. So we can say that dy dx, the derivative, is equal to tangent of theta, which means that dy is equal to just tangent of theta dx. And that gives us our dl vector. Dx we left by itself. Dy we said was tangent of theta times dx, which means we're ready to set up the cross product that appears in our force equation, dl cross b. Setting up the cross product, I like to do this, the determinant of this 3x3 matrix, I hat, j hat, k hat. dl was dx in the I hat direction, tangent of theta dx in the j hat direction. The b field is pointing just in the j hat direction. So when I take the cross product, there's no k hat component. Sorry, there's no I hat component, nor is there a j hat component. There's only the k hat component, and that's given by v naught times dx, pointing in the k hat direction. And again, it sounds like an easy mistake, but it's happened. I definitely lost points for this in Phys 2 when I took it. Don't forget to multiply by the I to find your differential torque. You're not, sorry, differential force. You're not done when you take the cross product. You need to include the I in there. You can also include the I just out in front here, and then you would have an I here and an I here. Whatever works best for you. But as long as you include it in the end to find your differential force as I b naught dx in the k hat direction. Cool. Now, hypothetically, we could take this differential force and integrate it to find the total force, but that's just a hassle that I don't want to deal with right now because we're not asking for torque. We're not asking for force, we're asking for torque. So now is where we do the cross product. For the second cross product, this is wrong, by the way, this is a typo. That should be force, df rather. Yeah, df is equal to I dl cross b, which we just determined was I b naught dx in the k hat direction. Now let's figure out what our r vector is. So let me go back to the picture. It's rotating about the y-axis. This y-axis is our axis rotation. So then the r vector, as with all torque problems, points from this axis rotation to the point where force is being applied. And force is just being applied along that wire. All right then. So my r vector, it doesn't point anything in the j hat direction. It's just strictly horizontal. So we know it only has an I hat component. What is that I hat component? What is that distance of the r vector? Well, it's just x, because that r vector is pointing to the line, and we're keeping everything in terms of x. So that distance, we can just say, is whatever the x coordinate is on that line. Since the r vector, maybe if we drew it differently down here, that distance would again just be the corresponding x distance. Again, this distance is a new corresponding x distance. Regardless, in variable form, we can say that our r vector is always just x times I hat. Super. Now we're ready to set up the second cross product. d tau is equal to r cross df. We have x I hat 0, 0, then 0, 0 I b naught dx. Taking that cross product, we only get something in the j hat direction. And remember, we subtract away the j hat component. Just remember to review how to take cross products, but don't forget that negative sign. We get negative I b naught x times dx in the j hat direction. We're almost done. We just have one step left. Now that we have our differential torque, we can integrate to find total torque. And we're integrating with respect to x. That's what we did at the very, very beginning, where we had to express dy in terms of dx so that we can take this integral. Well, now it's important. Now that everything's in terms of x, we can just set up an integral. Torque is the integral of the differential torque. And since we're integrating with respect to x, the bounds of integration will inherit the smallest and largest x coordinates. So if we look back at the picture, x started right here at 0, and the large x coordinate was all the way over here at L cosine theta. So those are my bounds. And that's just, these are just constants rather. Integrating with respect to x gives us x squared over 2. Then I plug in my bounds and that should be it. Any questions about that? Cool. And that's great timing that we got done with the 3 examples before 9 o'clock. But I'm happy. I don't know about you. I won't speak for you, Tyler, but I'm happy to stay further and keep working on things.
Yeah, I've got probably about 10 minutes, then I'll take off. So
Sure.
yeah, appreciate it.
I'm happy
Yeah.
to keep working. We can just, I can take whatever was second place or next in the poll.
Yeah,
If
all
whatever-
good. Thanks for helping me work through stuff, Nick. I really appreciate it. I think this went pretty well. Those of you still left, can you guys comment on the fact of whether or not this was useful? If you guys enjoy these sorts of things, as in we should keep the format or change it up a bit? What would you like to see in the future? But other than that, yeah, feel free to ask about any of the examples you'd like to see gone over, and we'll go through them. So go right ahead.
And to answer the question in the chat before it got buried, do you think a torque problem could be one of the free response questions? Absolutely. It definitely could be. I think, yeah, Tyler, I think you put your bets on it being an Ampere's law problem. I'm actually going to put my bets on this, on there being a torque problem for the free response. So it's,
I really, Nick, I pray that it's not a torque problem because I don't want to grade that shit. But it absolutely could be. Yeah, there's no telling what Pat's cooking up, but it very well may be. If I was more awake, this would have been awesome. Well, we appreciate it. Everybody's tired, man. No, or Brendan, no worries, man. We appreciate you showing up.
could we do Ampere's law if there's time? Yeah, we can absolutely go through that. It looks like enough people are staying, so I'm happy to just start working on them now. And Tyler or Kate, if you want to head out. Are you good with that, Tyler?
Oh yeah, sorry. Go right ahead.
Yeah.
Go ahead.
Oh yeah. Cool. Sorry.
No, all good. All good.
Let me pull up the Ampere's law problem. I think that was next in the polls anyway. Ampere's law.
Yeah, it definitely.
It was pretty close between Ampere's law and Faraday's law. We can definitely.
Yeah, actually, Nick, I realized I actually haven't had dinner, so I'm going to take off. But yeah, I'm really glad you guys enjoyed all this. We'll be having the next one sometime, obviously, before the final. Feel free to send either of us or Kate as well an email if you have any lingering questions. There will still be office hours on Monday, so just make sure you don't forget about that exam. It'll be all remote. All right, you guys have a good night. All right.
Cool. In which case, I'll start working through Ampere's law. If I reshare my screen and I scroll up to the problem, oops, it's not there. Yeah, here it is. If you want to follow along, I think I'm sharing. Yeah. So if you want to follow along, this is on page 18 of the slides that I posted. We have a wire with radius A, and it's carrying a uniform current I naught. That's this gray part right here. And we also have an annular cylinder. That's just a funky phrase, or I guess you can say that this shape in general is called an annulus. So when you extrude it outwards, that's an annular cylinder. That's the outer sheath with inner radius B and outer radius C. That's also carrying a current. And let's say the inner wire of radius A is carrying a current of I naught. That's just a constant. By contrast, the annular cylinder, the outer gray thing, is carrying a current of, or sorry, it's carrying a current density. We don't know what its current is yet, of 1 over r squared. And we'll assume that the units work out. That current density, it's just amps per area, so amps per meter squared. So whatever the units on that constant one have to be. But regardless, we need to find the magnitude of the magnetic field using Ampere's law at a distance r from the center axis, where first, in part A, we want r is less than a, so we want it in here. For part B, we want r in between a and b, so in this hollow section right there. For part C, we want our Amperian loop to be nested inside the annular cylinder. And for part D, we want it all the way outside. Whoops, badly drawn, but all the way outside. All right, let's go forward. So Ampere's law reads, we have the integral, the closed loop integral of b dot dl is equal to mu naught times I through. And we need to figure out what the magnitude of the magnetic field at a distance r is away from the center axis. Again, this was going back to the question earlier when Tyler got asked, when Tyler was going over Ampere's law, what r is equal to. R is just how we apply it in Ampere's law. It's the distance at which we want the B field. So it's going to be the radius of the Amperian loop. Our first step in using Ampere's law, I like to start with finding the current enclosed by that Amperian loop. So let's just go down the line. Let's start with part A and figure out what the current is enclosed is when R is smaller than the inner wire. So when R is inside here. Okay, so for part A, well, we're told that the inner wire carries a uniform current I naught. Whenever current is uniform, we can say that the current density is just a constant. Current density for a uniform current is just going to be whatever the total current is, that's meant to be an I naught, divided by the total cross-sectional area. And the total cross-sectional area through which that current is flowing, well, that's just a circle. It's a circle with radius a, so it's going to be I naught over pi a squared. We can take the integral of j dA to find the enclosed current. And taking the integral gives us, we have the integral of j dot dA. J is a constant. That's because the current was uniformly distributed, so we can just pull it out of the integral. And A is or rather dA. Well, we're dealing with a circular cross-section. So as Tyler was saying earlier, area is pi r squared, so we can take a derivative to figure out what dA is. If area is pi r squared, taking a derivative with respect to r gives us dA as 2 pi r times dr. Now here's the other subtle point with Ampere's law. I want the B field at a distance r. Again, my r is in between, it starts at the origin, and my r just extends outwards to some Amperian loop that's inside this inner wire right there. So r, the radius at which I want my B field, is a distance. But just to distinguish it from a variable of integration, I'm just going to put these little primes on the other r's. Those primes don't really mean anything. They're just meant to distinguish the r that's my upper bound. That's the limit of where current is being enclosed. It's not being enclosed past my Amperian loop. These little r primes, those are just variables of integration. They're just going to go away. Well, 2 pi is a constant, so that comes out of the integral. And then integrating r prime dr gives us r squared over 2, which when I plug in my upper bound r, that's the radius at which I want my Amperian loop, I get I naught times r squared over a squared. Let's do a gut check. Does that make sense? Well, for part A, when I want the B field inside the center conductor, my r is going to be smaller than a. So there's just no way I'm going to enclose any more current than I naught. I naught is like the maximum amount of current I can enclose. And indeed, the current enclosed is just that value times this ratio. And this ratio is going to be necessarily smaller than 1, just because a squared has to be bigger than r squared for part A. Cool. Now let's move on to part B. Find the current enclosed when now for part B, our R is in between, it's nested in between those two conductors. It still has radius R, but now R is in between A and B. Obviously I can just look at this problem and say, okay, well, if this is my Amperian loop, it's in between A and B. The current enclosed is just the current that the inner wire carries, I naught. Let's just make sure that's what we get when we take an integral, just to make sure we're not going crazy or anything. If I set up my integral the same way as before, it's the same current density, except now my upper bound of integration is A, because again, if I return to my picture, I'm integrating with respect to R, a radial distance. So I start here, keep moving, then I hit A. I'm not enclosing any current past A, so I have to set A to be my upper bound of integration. I'm not enclosing any current past my radius A. And indeed, if I take that same integral and instead of plugging in R for that upper bound, I plug in A, well, I get the same thing, but the A's cancel. And I get that the current enclosed is the current enclosed. That's reassuring. Cool. Now let's do part C. Here we have a completely new beast. So if I go back to the picture and erase this R for part B, for part C, my R is nested in between these two conductors. It's nested inside this annular cylinder. So that's my R right there. I'm sorry it's not a smooth circle, but it's kind of hard to draw with the mouse. That's my R. So I want to find the B field at that R, which means I need to find the current enclosed when my R is in between B and C. The current enclosed, it still carries that inner current from before. We still have that I naught that we carried previously because that inner wire is still inside that annular cylinder. But now for the current carried by the annular cylinder, we have this whole new integral. It's still the integral of J dot dA, except we're given now what the J is for the annular cylinder. It's 1 over R squared. And as before, it's a circular cross section. So dA we can just say is 2 pi R dr. Pretty much, I can't think of an exception. Every time you deal with Phys 2, in Phys 2, dealing with dAs for Ampere's law, it's going to be a circle. So there's going to be a circular cross section, and dA is going to be 2 pi R dr. Nifty. So let's erase that. I naught, that just stays. And then 2 pi is a constant. I'll pull that out of the integral. One of the r's cancels. And I'm left with the integral of dr. Sorry, I'm left with the integral of 1 over r integrated with respect to r. Now my bounds of integration, I have to be super careful. My bounds of integration are from b to r. The reason being is because, again, I'm integrating with respect to a radial distance. And that current density that I'm given, the 1 over r squared, it only applies in this region right there, in the annular cylinder. So I can only integrate that when I'm enclosing current within that annular cylinder. So I'm moving along this radial distance. Then, oops, I hit this annular cylinder at r equals b. So that's my lower bound. And then I stop enclosing current at the upper bound of my Amperian loop, which is just the distance r at which I want the B field. All right. Any questions about those bounds? that's sometimes a confusing point. Cool. If there's anything, just post it in the chat and I'll be happy to look at it. So those are my bounds of integration from B to R. And when I take that integral, it's the integral of 1 over R, so that's just the natural log. I'm gonna turn on the lights real quick so I can see. I'll be right back. Sorry about that. Cool, so I have to take this integral from B to R of 1 over R, that's the natural log, the 2 pi stays, and I have natural log of R over B. Awesome, now I just have one more part to do. In part D, my my Amperian loop is going to be all the way outside because my R is bigger than the C. So that's my Amperian loop. That's my radius R at which I want the B field. And it's going to be very close to what part C was, where I still enclose my inner wire of radius A, but now I have to take a new integral for my JDA. Now the bounds of integration are from B to C, because if I'm integrating with respect to a radius, I start enclosing current at R is equal to B for that new current density that I'm given, and then I stop at C. I'm not enclosing any current past C, even though my R extends past C. So those are my bounds of integration. Cool. And it's the same integral as before. The 2 pi comes out, one of the r's cancels. The integral of 1 over r is the natural log, and then I now have c over b instead of r over b. Now for all of these, what we just did was we took care of the right-hand side of Ampere's law, because if I scroll to the very top with what Ampere's law is, we took care of the right-hand side by figuring out what I enclosed was. Now we need the left-hand side to actually solve for what the B field is. What's nice about all these problems is that the appropriate symmetry arguments hold. If I go to, which one? Here it is. Yeah, this diagram applies to just a current carrying wire, but it's the same principle even if it isn't just a thin wire and it has some thicker radius A. We still have this curly B field going around it, and no matter how I draw my circular Amperian loop, if I draw a circular Amperian loop, I have that my dl vectors are parallel to my B field vectors. So the dot product between them goes away. And I have that my B is uniform along my Amperian loop. So B can come out of the integral and I'm left with the length of the Amperian loop. All right. So that takes care of the left-hand side for all 4 of my situations. I have B times the length of the Amperian loop, which is a circle, so that's just 2 pi r. For part A, when I put everything together, I have the left-hand side, the right-hand side, just divide over to find what my B field is. For part B, same thing. This time the current enclosed was just I naught, which what we just derived essentially here is the equation that we have on our equation sheet for a current carrying loop. For part C, this one was a little bit more tricky, but regardless, finishing it up is still the same. That's our current through that we found by integrating. Divide over by 2 pi r. And for part D, the exact same thing, except now we use C over B. How's that all sound? Of course. Does the distinction between the R that I use for my radius of the Amperian loop and the integration R make sense? Super. Cool. something to put on mask. Give me a second to pull up a Faraday's law problem because that was the Kate, if you have any problems you want to work on, or if you want to do something, let me know. Yeah. Let's see. Let me find a Faraday's law problem. We should probably not do something that's from the 2011 test because Pat made a whole video about that. So give me a quick second and I'll come up with a good problem. Hold on. Okay, I found a good problem. So let's let me reshare my screen. Here it is. This round is called spinning loop. I don't think you guys have access to it yet because this isn't the final exam practice questions, but it's the only one I can find right now that I have neatly typed. So I guess we'll deal with that. So let's say we have a B field and it's pointing into this page as indicated by these X's here. Let me actually download this document so I can draw on it. Here it is. And that was on page. Where'd it go? Here it is. All right, we have a n loops of wire rotating about an axis with some angular speed omega, and there's a uniform magnetic field B pointing into the page, as indicated by those B's right there. I want to find the magnitude of the induced EMF in the spinning loop. All right. So it's going to be a Faraday's law problem because we have a loop that's an area, and the amount of flux through that loop is changing with respect to time because I'm spinning that loop. So as that loop spins, maybe as it's shown right here, you have a maximum amount of flux going through it, but then sometime later, it's sort of on its side, but the B field is still pointing into the page, so there's not as much flux. And then sometime after that, the loop is completely straight, so there's no flux at all. We need to somehow figure out how we can get Faraday's law to get us the induced EMF in that loop. All right. Well, Faraday's law tells us that the induced EMF is just going to be the time derivative of the magnetic flux. So the time derivative of whatever this integral comes out to be. Thankfully, we don't have to take an integral. The reason we don't is because this B field is completely uniform. It doesn't change with respect to space. It's just B everywhere throughout. And this loop, the area of the loop is changing because it's being rotated, but the loop itself, it's just a circle. So we can say that the area of the loop is pi r squared. What does change rather, and how we can account for the fact that the loop is rotating is with the dot product in the definition of flux. So flux is defined to be the dot product of B dot dA. It's a uniform B field through a nice neat area, so we don't have to take the integral, so that just comes out to be B dot A. And the area vector, or rather the dot product between the B field and the area vector, the dot product for any two vectors is just their magnitudes multiplied together times the cosine of the angle between them. And we're told that the loop is rotating at an angular frequency of omega. So if we think back to Phys 1, we can say that the angle theta is just given by omega times t, if you remember that relationship. Sort of how distance is just position. Position is just velocity times time. The angular version is that the angles are theta is equal to omega times t. So in full, what this flux comes out to, if it's just b times a times cosine of theta, we have to take into account the n number of turns, but we have b times the area times the cosine of omega t. Faraday's law just tells us to take a derivative of that quantity, so let's do that. N, b, and a are all constants with respect to time, so they come out of the derivative. And then taking the derivative of cosine with respect to time, we pull out the factor of omega, and that integral becomes a sine. The reason why, that cosine becomes a sine. The reason why I crossed it off and said it's just equal to 1 here is because I think the original problem was telling us to find the maximum induced EMF, and sine, as with trig functions, is going to max out at 1, so we can just ignore trig terms. So that's the maximum induced EMF. The number of turns times the B field times 2 times pi r squared for the area times omega. How's that sound for Faraday's law? Any questions there? Cool. There's still enough of you, so I'm happy to keep going. Let's see, what was next in the chat? Or what was next in the poll? The Biot-Savart law, which we did. Ampere's law we did. Magnetic forces. Yeah, I think magnetic forces is the only one we haven't done that was in the poll, so let's do that. If I close out of that, and okay, I guess the chat question was a tiny bit ambiguous. Do you want to do forces on current carrying wires, or do you want to do forces on charges? Or both? I'm happy to do both. Okay, if there's no preference, I'll just start with forces on particles. Oh, I got a reply. Okay, cool, both. Yeah, let's just start then with forces on particles. And to that end, I made up a problem. So let me reshare my screen. Here it is. It's called Worked Example Mystery Particle. So a magnetic field of 150 milliteslas is pointing out of the page. And just for context, that's about the strength of a sunspot. An unknown particle is moving in a counterclockwise circular path of a pretty small radius, perpendicular to that magnetic field. So we have a magnetic field that's pointing out of the page. Let's make it blue so it's consistent with the colors that I've been using. We have a magnetic field that's pointing out of the page. So that's my B field. And then we have a particle that's moving in a circular counterclockwise path with a known radius. And if I impose an electric field of 44.2 kilovolts per meter, that makes the path straight. So now we're being told to find the charge to mass ratio of the particle. Okay. So there's two sort of things going on. There's two, I called it regimes for lack of a better word, but there's two regimes governing the motion of the particle. One in which the particle is moving in a circular path, and one in which it's moving in a straight path. So those are completely different scenarios. They have to be treated separately. Let's first look at the circular path thing. If it's moving in a circular path, the B field is providing the centripetal force that's pulling it in a circular path. And it's moving completely perpendicular to that to the B field. So it's just moving in a circle. We can just say then that the magnetic force, QV cross B, or rather its magnitude, is just equal to the magnitude of acceleration from Newton's second law, force is equal mass times v squared over r for angular acceleration. If I consider the magnitude of that cross product, well, they're perpendicular vectors, so I can just think about the multiplication. The v's cancel. I have q times v is equal to mv over r. And let me quickly remind myself what it was asking for. It was asking for the charge to mass ratio. Okay, I guess I'll solve for it just right now. Charge to mass ratio is just going to be v over b times r. I know the strength of my B field. I know the radius of the circular path because I was told how the radius it was traveling at, but I don't know its velocity, unfortunately. That's where the other regime of this problem comes into play. If something is moving in a straight path, if the particle's moving in a straight path, then Newton's first law asserts that anything moving in a straight path with constant velocity or constant speed must have zero force acting upon it. If there's no acceleration, there's no force, and it's just not going to change path. It's just moving in a straight line. And that's what's happening here. Then it must be the case that the magnetic force, or its magnitude, is completely balanced by the electric force. So we have QV cross B is equal to Q times E. The cross product goes away, the Q's cancel, and we get E is equal to V over B, which we know both of those. So we can solve, or sorry, we know both E and B, so we can solve for velocity, which we didn't know earlier. So this V is going to be substituted in that expression above. Putting it in, and I think this is another, yeah, that's a typo. That should be a division sign right there. I'm just using this expression right here. The charge to mass ratio is E over B squared times R. We're given some numbers, so let's plug those in. That was our E field, that's our B field squared, the radius of its path, and we get that for our final answer. But it's a trick, because that's not our final answer. Charge can be positive or negative, but what we've been considering so far, the charge either went away, as it did in the second regime, or what we did in the first regime where it was just moving in a circle, we only considered the magnitude of the charge. So that doesn't tell us much about how it was, or the sign of the final answer. Thankfully, we've been told that the particle is moving in a counterclockwise path perpendicular to a magnetic field that's pointing out of the page. So let's look at the right-hand rule. The right-hand rule, if you recall, is F is equal to QV cross B. So my thumb is my force, my index finger is the velocity, and my middle finger is the B field. If I scroll back down to the picture, here it is. As Tyler said, B, big finger, that's pointing out of the page, so that's pointing at me. My velocity, that's my index finger, it's pointing sort of counterclockwise. Yeah, counterclockwise. What I get is that my force is pointing in the wrong direction. Like what I'm looking at right now is this top vector right here. Let's do blue for the B field. That's my middle finger pointing out of the page. My middle finger is pointing out at me. My index finger is pointing to the left. which if I'm using my right hand, my thumb is pointing upwards, but that's wrong because we know that if something's moving in a circular path, the force is directed inwards. So all that tells us is that the charge is negative. We have to flip the signs, and here's our final answer. And in case anyone was curious, the particle is an electron. I don't suspect the test will try to trick you like I did here. That was just a problem I made up yesterday, but it shouldn't be any trick questions like that. It was just something else to consider. How does that sound for one of the force problems? Anything need clarification or further explanation? Cool, I'll take that as no. Super. So let's do one more force problem. Let me reshare my screen real quick. Here it is. All right. The other force equation that we have on our equation sheet is for current carrying wires as opposed to charges. That force equation is dF equals IDL cross B. So let's do a problem about that. Okay. Let's suppose I have two perpendicular wires as shown. There's an infinite wire with current I1 flowing from left to right, and a wire stub right here on the bottom flowing towards the top of the page, with current I2 flowing towards the top of the page. And there's a gap of length D in between the two wires. I want the force on wire 2, the force on that wire right there, due to the B field produced by wire 1. Okay. Thankfully, wire 1 is an infinite wire, and we have equations for the B fields produced by infinite wires. As it stands on our equation sheet, the B field produced by an infinite wire is just mu naught I over 2 pi r, where r is the distance away from that wire. But we're dealing with two wires here, and we're going to have to calculate the force on one from the other. So let's just impose a coordinate system. Let's say x-axis is pointing to the right, y-axis is pointing up, and the z-axis is pointing out towards the page towards us. And the origin of this coordinate system is centered directly above that wire stub right there. Okay, in that case, if we're going to be using this coordinate system to take cross products and everything, we can re-express our B field equation of the infinite wire as mu naught still. And then the current that's in that infinite wire is I1, 2 pi. Now here's where things get a tiny bit tricky. No, not tricky, we just have to be careful. The y-axis points up on the page, but the wire stub is below the infinite wire in this coordinate system, so we have to include this negative y here. And let's consider the direction the B field is. So if I pull up my infinite wire thing, here it is, and I make it such that, oh, that's a bit busy, such that the current is flowing to the right as it was for wire 1, then sort of out here in front of that wire kind of towards us, those B field vectors are pointing straight down. That's probably a bit too busy of a picture, but all those B field vectors are pointing into the page. So if I go back here, oops, the B field, due to the infinite wire in the vicinity of this wire stub, is just pointing into that page. That's what I called B1 right there. And again, I'm trying to express the B field of my infinite wire. We said that was pointing, or it was in the negative y direction, so that's there. If it's pointing into the page, that's in the negative z direction, so I have to include this negative k hat at the end right there. Oop, right there. Cool, those two negative signs cancel. And we get, here I wrote out basically the whole same thing. We have negative y in the, because the wire stub is below the infinite wire, and it's pointing in the negative k hat direction, but the two negative signs cancel, and we just get that for our final B field expression. Let's check to make sure that makes sense. Let's consider some positive y value. If we had some positive y value, we would be up here. If I plugged in some positive number into y, well, this whole expression is positive. and I would get a k hat that's pointing out of the page. And indeed, if I use my right-hand rule, the B field from this infinite current carrying wire is pointing out of the page above it. This is also B1. Cool, that makes sense. Awesome. So we're using the force equation, which is dF is equal to I dl cross B. So we need to take a cross product. And this cross product, or rather this whole entire thing, I dl, it describes some infinitesimal piece of current or infinitesimal piece of wire of the wire that's subject to the force. So this IDL vector describes the wire stub because the wire stub is the thing that's experiencing the force. The wire stub is just pointing straight up on the page. So we can just say it's pointing, the DL is equal to dy since it's in the y direction, j hat. And taking the cross product, we have df is equal to I2 dl cross B1. That's our IDL, that's our B field. The cross product of j hat and k hat is just I hat. We don't even have to set up a matrix here. I can sort of check that with my right hand rule, or with my right hand. If I go back to my coordinate system, j hat being my first vector, k hat being my second vector. Oh yeah, sorry. Yeah, no, that's good. J hat is my index finger that's pointing up. K hat is my middle finger that's pointing out of the page towards me. So my thumb is pointing to the right, that's I hat. So I have j hat cross k hat is equal to I hat. And I think Pat has some other rule for remembering how those go, but I don't know Pat's way. Either way, here's our df expression. For the cross product, we just get I hat, and then we multiply everything else together. So we have mu naught I1, I2 over 2 pi y dy. That gave us the differential force, but we don't want the total force. So we have to integrate to find the total force. We're integrating with respect to y. And as always, what we do in Phys 2 is, or not just in Phys 2, in physics in general, is if we're integrating with respect to y, we want our bounds of integration to inherit the smallest and largest values of y respectively. Our y values, they start way at the bottom here at negative d plus l, and they move up to just d. If I just get rid of the negative signs, that's what it comes out to here. D plus L for the lower bound and D for my upper bound. I stick that in there. Mu naught I1, I2, and 2 pi are all constants. Those come out. Then I have the integral of 1 over y, which is just a natural log. I can rewrite the natural log by making it negative and then flipping what's inside of it to find that for my total force equation. Let's do a gut check to make sure everything came out okay. Using this right-hand rule right here, if my IDL vector is pointing in the direction of the wire stub, that's my index finger. So my index finger is pointing up on the page. My B field is pointing into the page. That's my middle finger. My thumb is indeed pointing sort of backwards or to the left. So I should indeed get a force that's in the negative I hat direction.
Quick question.
Yeah.
When you got those bounds, you just got rid of the negative so that it was like easier to work through, but then remembered to like re-include them at the end? Is that how you got the switching of the ln?
Now that I'm looking at it, I probably goofed a little bit. So okay, just regardless, in a global way, I can answer. I can say that if you're asked a problem similar to this on the test, I don't suspect they'll actually want you to find the direction of the force. They'll at most want you to find the magnitude and maybe the direction you can compute sort of manually with the right-hand rule. But as far as the bounds, I probably goofed a little bit because if I set my coordinate system such that I had my z-axis pointing out of the page, my my y-axis pointing up and my x pointing to the left, or sorry, to the right. And then my wire stub was here. What I probably should have done was set my lower bound to minus d plus L. Oops. Minus d over L, because that was my smallest y coordinate there. Since these are they're technically negative y values since it's below the origin of the coordinate system. At which point everything would have been the same. I would just have negative signs right here and here, which would cancel, and I would have gotten the same answer. The reason why I have d plus L on the bottom as my lower bound and d at the top is because d plus L, or I guess what it should be as negative d plus L, is my it's a smaller value, so it's my lower bound. It's like the smaller y value. I don't know how coherent that was or if that made any sense.
Yeah, it's all good. Thank
Okay.
you.
Regardless, if you got a question like this, my recommendation, my advice would be to avoid trying to determine the direction of the force using math, even though the math does work itself out and you get the right answer. Avoid trying to find the direction of the force using math, just compute the magnitude of the force. And then to find the direction of the force, you can just use simple F equals IL cross B with the right-hand rule that we've been using. All right, what else can I help with? You can go through any other of the problems that are in the slides, or I'm happy to do whatever. Also, Kate, if you want to eat dinner, I'm happy. There's not too many people left, so I'm happy to take over.
Hey man, all I was gonna say is you might be overworking yourself.
No,
They
I'm
can
fine.
come back and watch this, and then there's gonna be studio tomorrow for additional questions along those lines. So if you feel good about it, you've covered everything, and they can come back and watch it. So
Awesome. Yeah, studio tomorrow. Feel free to ask questions then, and then office hours on Monday. Definitely go to those if you want to, and yeah, test on Tuesday. Cool. I'm gonna stop recording because it doesn't look like we're gonna do any more. Where's that button? There it is.